Okay, we'll continue our review of equilibrium, looking at LeChatelier's principle. Again, some of the example problems I'm going to use come from the book, or at least are inspired by the book, Chemistry from Riddell and Navidi, West Publishing, 1990. It was a book I had available on my bookshelf. So, LeChatelier's principle, right, is important because LeChatelier's principle applies across a number of disciplines, right? It's about equilibrium. It was discovered in chemistry, but it really applies in sociology and in psychology and in biology and in chemistry and economics, right? LeChatelier's principle applies across a wide variety of subject matters. And LeChatelier's principle is this, right? When a stress is placed on a system in equilibrium, the system will act to relieve the stress to find a new equilibrium position. Right? That is a very important principle. And it's why, right, for those of you who've been around me for a while, know that, right? LeChatelier is our second favorite dead French chemist. Right? And for those of you who've been around, you should know who the favorite dead French chemist is. Okay, so here we have a system that we've looked at in a previous video on equilibrium. Here we have dinitrogen tetroxide gas, which ends up being a colorless gas, and it forms an equilibrium with nitrogen dioxide gas, which is a reddish-brown gas. And so we can see the effect of these gases based on the color of the mixture. And so here we have an equilibrium constant in concentration terms at two different temperatures. I don't know why I made my little c so small there. Let's just fix that so it looks better, right? Degrees Celsius. Right? So, right here we have our reaction, and we have two different equilibrium constants. And so we notice at the higher temperature, our equilibrium constant is larger, which means at the higher temperature, we're moving a little farther toward products. So we have a little more products on the product side and a little less on the reactant side at the higher temperature. And so now what is going to happen to the equilibrium if we make some changes, right? So if we start here, so let's make, choice A, right? Let's deal with that temperature. What is going to happen to the equilibrium if we increase the temperature? Well, we just said if we increase the temperature, our equilibrium will be shifted farther to the right than to the left, right? That's what that difference in equilibrium constants tells us, that an increase in temperature pushes our equilibrium farther to the right. And so we end up then with this higher value of the equilibrium constant at the higher temperature, okay? So, our next possible change is what happens if we increase the concentration of dinitrogen tetroxide suddenly. Okay? So in this case, we had a system that was in equilibrium, and then we suddenly add some dinitrogen tetroxide. And so the stress on the equilibrium is too much, right? Too much dinitrogen tetroxide. And so the system then will react to reduce the amount of dinitrogen tetroxide. And so we will use up some dinitrogen tetroxide, right? Which will make more nitrogen dioxide. And so that change will also shift our equilibrium to the right to use up the extra dinitrogen tetroxide, which will force us to make more nitrogen dioxide to reach a new equilibrium position. Okay? C, right? What if we increase the partial pressure of nitrogen dioxide? Well, remember, pressure is another way of measuring the concentration of things in the gas phase. So if we were at equilibrium and we suddenly increase the pressure of nitrogen dioxide by adding more nitrogen dioxide, then our problem is going to be too much nitrogen dioxide. The system will need to reduce that number. And the only way it can reduce the amount of nitrogen dioxide is to shift toward the left. The equilibrium would shift toward the left. We would use up the extra nitrogen dioxide. Make my arrows a little better there. Would use up the extra nitrogen dioxide. The reaction would shift toward the left to make more dinitrogen tetroxide until the reaction reaches a new equilibrium position. Right? So, right? D, oh, wrong one. So D would be if we add helium to increase the total pressure. Well, if we added helium, right, it would increase the total pressure because the total pressure, according to our second favorite dead English junior high teacher, right, Dalton, and Dalton's law of partial pressure, right, the total pressure would then be the partial pressure of the dinitrogen tetroxide plus the partial pressure of the nitrogen dioxide plus the partial pressure of the helium. But helium adding to the total pressure will not change the partial pressures of the participants in the reaction. And if those pressures don't change, then the equilibrium constant in pressure terms can't change. And so this would have no effect on our equilibrium, right? Adding an unrelated gas doesn't affect the equilibrium of the gases that are there if nothing else changes, right? And then they ask a final question, right? Based on what we see, can we tell whether this reaction is endothermic? That is, does it absorb heat? That is, delta H for the reaction is negative. or is it exothermic? Does it release heat? Actually, I got that backwards, right? This is what happens when you write faster than you think. Endothermic absorbs heat, so delta H0 is positive, right? Let's get this straight, right? Sometimes we speak faster than we think, right? So there's more heat stored in the 2 moles of nitrogen dioxide than there was in the 1 mole of dinitrogen tetroxide, right? Or is it exothermic? That is, does it release heat that is delta H for the reaction is a negative number. Okay, now we've got that straight, right? Sometimes we learn more from screwing it up. All right, so let's go back up here and look at the effect on our equilibrium constant of the temperature, right? At a higher temperature, we move the reaction farther toward products, right? So more heat around pushes our reaction toward products, right? So if we imagine heat as a reactant or product, more heat moving toward products would put heat on this side of the reaction. Because if we increase the temperature, right, we see if we increase the temperature, we push the reaction toward the right, which means if heat is the stress on our equilibrium, then the system will react to relieve that stress, absorb heat, and store that heat in the molecules of the product. That means, right, there's more heat energy stored in the products than in the reactants, and that is going to make, right, delta H0 positive, and the reaction is going to be endothermic. It is going to absorb heat energy. Now, here we're going to consider a reaction going on in aqueous solution. We've got the dichromate ion in aqueous solution, which is orange. I didn't have an orange pen, so I had to use red. In the basic solution, the dichromate will react with hydroxide ion to form the chromate ion, which is yellow, plus water. Right? And so this is an equilibrium, and you can tell the equilibrium position by looking at the color of the solution, right? And so our first question is, what's going to happen to our reaction if we add sodium hydroxide, right? If we add sodium hydroxide, we know that sodium hydroxide, when we put it in water, is a strong electrolyte, and it will dissociate into sodium ions and hydroxide ions, right? Those hydroxide ions will add to the number of hydroxide ions in solution. Our stress will be too many or too high a concentration of hydroxide ions. To relieve that stress, the reaction will need to consume some of those by moving to the right. And so our reaction then our equilibrium would shift to the right, farther to the right. Our concentration of dichromate ions would go down. Our concentration of chromate ions would go up. And so our solution would get more yellow, less orange. Okay? And so, right, our B situation, what if we add some hydrogen chloride or hydrochloric acid to our reaction mixture? Well, our hydrochloric acid will react with our hydroxide ions to make water, which is, right, remember this is a pure liquid, so its activity is 1, so we're not worried about that. So we've got liquid water. That's not going to affect things because it's going to be taken up in the solvent plus chloride ions. But what is going to affect the equilibrium is the fact that we're using up hydroxide ions. And so the stress on our equilibrium is going to be too few, or a lower concentration of hydroxide ions. The only way we can relieve that stress is to try to make more hydroxide ions, so that would shift our equilibrium back toward the reactant side, right? And so moving back toward the reactant side, even though we didn't add anything, to move back toward the reactant side, we would have to consume some of our chromate ion going back. That would make more of our dichromate ion, and so our reaction would get more orange and less yellow. And so we could see the effect of changing those concentrations of hydroxide ions in those ways, even though we never affected directly the concentrations of the chromium species by adding or subtracting those compounds. So there's an effect of LeChatelier's principle. Here's another reaction that I'm pretty sure we've seen before, right? Here's sulfur dioxide reacting with oxygen to make sulfur trioxide, right? And those gases are in equilibrium. And here we have a heat of reaction, right? An enthalpy change of negative 197 kilojoules. That is our reaction is exothermic, right? It is releasing heat energy, right? Which puts heat released on that product side, okay? So they give us two potential changes, right? So change one is we are going to compress this reaction by reducing the volume of the container, right? So imagine that we had the reaction, right, in a container with a movable wall, and then we push that wall down to reduce the volume of the container, okay? What is that going to do to this gaseous reaction, right? Well, essentially it's going to double the partial pressure of every gas, right? So, let's say we cut the volume of the container in half. That's going to double each concentration. So let's look at the effect on the equilibrium constant in pressure terms, right? Suddenly the pressure, right? So if the equilibrium constant in pressure terms is the pressure of sulfur trioxide squared divided by the pressure of sulfur dioxide squared times the pressure of oxygen to the first, right? That's the expression of our K under pressure terms. Okay, so let's look at this. We compress this. Let's look at Q, right? let's assume we're not at equilibrium, right? Each pressure will double if we cut the volume in half. So that would be 2 times the pressure of sulfur trioxide. I can do this. Let's fix that. All right, go back to this. Sulfur trioxide. That would all be squared, right, because the pressure doubled, divided by 2 times the pressure of sulfur dioxide squared. And again, let's make this clear. This would all be squared times the pressure of oxygen. And I have to remember this, right? The pressure of oxygen would be doubled too, right? So 2 times the pressure of oxygen. But we don't have to square it. But if we expand this, we have 4 times the pressure of sulfur trioxide squared divided by 4 times the pressure of sulfur dioxide squared times 2 times the pressure of oxygen. Well, here we go, right? We've done our math, right? 4 divided by 4 is, that takes itself out. But we've still got this 2 here, right? And so the rest of this are the terms of our equilibrium constant. So our Q is equal to 1/2 of our equilibrium constant in pressure terms. That is, Q is less than the equilibrium constant. Q is too small in this case. Because Q is too small, we have to move the reaction toward making more products to make Q bigger and less reactants that will also make Q bigger. And so that says then that reducing that concentration would shift our equilibrium farther to the right because Q is too small when we compressed that reaction. Right? In our last case, again, we have an exothermic reaction, right? So B, right, what happens if we increase the temperature, right? What's going to happen if we increase the temperature of our reaction? Well, increasing the temperature means, right, heat is added, right? Since we said this reaction is exothermic, heat appears on this side. So if we have extra heat, the only way the reaction can reduce that extra heat affecting the equilibrium is to absorb that heat by having the reaction go backwards, right? So to remove the excess heat, the reaction has to absorb heat by shifting backwards. And so the effect on the equilibrium is to shift the equilibrium back toward reactants and away from products. So I hope these videos have helped you with some equilibrium concepts as you prepare for your next exam. Thank you.